Hello everyone, welcome back to IITian Club. I am Ashlin M L, first year student at NIT Calicut. Today, we will be quickly covering the entire chapter of chemical kinetics in one shot. Without wasting our time, let's start. First of all, we should know what is the rate of a reaction. Consider the given reaction, that is A plus B giving C plus D. In this, we can define rate of reaction in two ways. One is as rate of disappearance of reactants, and other way is rate of appearance of products. Rate of disappearance of reactants will be denoting it as minus D of concentration of A. That square bracket denotes concentration of A. Minus denotes that A is disappearing. Same goes with B. Minus D concentration of B with respect to time. Rate of change of A with respect to time. That is decreasing, so the minusing. Similarly, for appearance of products, it is rate of change of C with respect to time and rate of change of D with respect to time. You should also note the relationship between individual rates. That is minus 1 by coefficient, stoichiometric coefficient. Minus 1 by A, dA by dt is equal to minus 1 by B, dB by dt is equal to 1 by C, dC by dt is equal to 1 by D, dD by dt. Everything you are dividing the individual rates with its stoichiometric coefficient. The next one is rate law. This is just an expression. Let's say you are having a reaction A plus A giving C plus D. What it says is rate is actually directly proportional to concentration of A to the power X, concentration of B to the power X. In here, X and Y may or may not be stoichiometric coefficients that we will be determining using different methods. When we remove the proportionality limit, we will be introducing K. K is the rate constant. Rate constant, you should note that it depends only on the temperature. It does not depend on any other parameter. And how it depends on the temperature, we will be looking at the end of this video in the Arrhenius theory. The next most important thing, that is order of reaction. We'll be analyzing the order of the reaction to the great extent in this chapter, and order of reaction is just the sum of exponents in the rate law, that is x plus y in this rate expression. I hope you got it. Moving on, we have different methods to analyze rate of reaction. We'll be going through 5 different methods to analyze the rate of reaction, starting with initial rate method. I will help you understand this method with a recent PYQ. This way you will be understanding the concept as well as solving a question. So let's start. Consider the following data for the given reaction. They have given us a reaction, that is HI is decomposing into hydrogen and iodine. And what they have given is, they have given different rates for different initial concentration. For different concentrations of HI, we'll be getting different rates. We know that for a reaction like this, rate is given by K into concentration to the power X's and Y's. And they have asked us order of reaction. Order of reaction is just the sum of X and Y. So, if we find X and Y, we'll be able to solve this question. We'll be writing the rate expression for this given chemical reaction as rate is equal to K into concentration of HI, that is concentration of the reactants. Here we have only one reactant, that is HI, raised to the power P. And we'll be taking 2 different cases, that for 2 different concentration we'll be having 2 different rates. And when we divide this expression, we'll be getting this. We know the value of R, we know the value of R2, we know the concentration at 1, concentration at 2. We have been given actually excess data over here. They have provided us 3 different data. We can use any 2 of them. I'll be selecting the first 2. And P will be the order of reaction, because here sum of every coefficient will be P plus 0. There is no other reactant, so only P will be there in this order of reaction. If we find P, we'll be able to find the order of the reaction while substituting the values of first and the second one. 3 into 10 to the power minus 3 divided by 7.5 into 10 to the power minus 4 is equal to 0.01 divided by 0.005 raised to the power n. N is actually P over here. And when we do the calculations, we'll be getting N as 2. So, order of this reaction is 2. Now, we will quickly summarize the initial rate law method. We will be given different initial rates of the reaction for different concentration. We will be given with different concentrations of A, for which we will be having different rates. And like this, we will be having different concentration of B and different rate will be there. We can write rate as K into concentration of A raised to the power P, concentration of B raised to the power Q, concentration of C raised to the power R. And in both cases, what we will be ensuring is only the concentration of A will be changing and concentration of B and C will be remaining same. So when we divide these both expressions, we will be able to find out P. Similarly, we will be able to find out Q when we will be having A and C as constants over here. The concentration of A and concentration of C will be constant in this case, and we'll be taking two different rates such that we'll be given with different data. When we see the next question, you'll be understanding that one. Similarly for C, and from this we'll be able to find out P, Q and R. When you sum it up, we'll be getting the order. That's the concept behind that. We'll be quickly revising this concept using two PYQs. Starting with this 2021 question. Here they have given us a reaction. NO plus H2 is giving us N2 and N2O. They have given us different concentrations of NO and different concentration of H2, and for that we have been given with different rates. Now what they have asked is the order of the reaction with respect to NO. You have to note that they have not asked the entire order. They have asked the order of the reaction with respect to NO. So what we have to basically find is the P over there. When you write the rate law as K into concentration of NO raised to the power P and H2 raised to Q. Over here we have to just find the P. Then what we have to do over here is you have to take the first two datas and into 10 to the power minus 5 and 24 into 10 to the power minus 5. H2 will be same, and when you divide the rate law for two steps, then it will be gone. Then you can easily substitute and find. I want you guys to try this and let me know in the comment. You will be getting the answer as 1. The next question is from 2019, where 2A plus B is giving us different products. Even here they have given with us different concentration of A and different concentration of B, and they have given us different rates. The same thing we have to use. But the thing is, they have asked the time in minutes required to consume half of A. This is basically the half-life concept. This you will be able to answer once you do the half-life method. But before that, the first thing to find over here is the order. That order we'll be finding using the initial rate law. That you can just find out here. Once you watch how to find half-life in this video, you can come back and do this question and let us know in the comments. The answer will be 10. I hope you will try these and let us know. And for the detailed solution of those two questions, you can join our Telegram channel. I'll be posting the answer in 2 days so that you can verify your solution and answer over there as well. Next, we'll be looking into the integrated rate law method. Suppose there is a reaction, like A is the reactant and it is giving some products. Any products be it. Then we can write rate as K into concentration of A to the power N. N will be denoting the order of the reaction over here. The same rate we can write as rate of change of A with respect to time equal to K into concentration of A to the power N. N is the order of the reaction. Suppose we are considering the zero order reaction. N will be 0, and for the first order reaction N will be 1. Now we will be looking into zero order reaction. Zero order reaction minus dA by dt is equal to K, because N becomes 0 and it will become 1, K into 1. So it will be K. And here we will be seeing that rate is constant. Rate is constant in the sense it does not depend upon the concentration. We will be looking that in first order reaction, rate will be depending on the concentration of A. In zero order reaction, rate is constant. It does not depend upon any concentration of reactants. Next, when we integrate this, that is when we bring dA and K dt to the other side and integrate, we will be getting the concentration of A as the reaction proceeds, as the time changes. That's what chemical kinetics basically is. We'll be analyzing the reaction at different times and analyzing the speed of the reaction as well. Now, we'll be getting the final result as concentration of A at any time t is equal to concentration of A at time equal to 0. That is initial concentration minus kT. This is just when we integrate this rate expression, we will be finally landing into the expression for concentration. I hope you got this. Now we'll be starting the first order reaction. Here rate of decrease of A, that is minus dA by dt, will be equal to K into concentration of A. N is equal to 1 over here, note that. And in this case, we will be seeing that rate is directly proportional to the concentration of A. Rate is equal to K into concentration of A. When we do integration over here, we will be getting the concentration expression, how the concentration changes with respect to time. That let's do now. dA by A is equal to minus k dt. And when you integrate from A0 to A0 is the concentration at time is equal to 0. That is initial concentration. A is the concentration at any time. Time equal to t. And when we do the integration, we'll be getting the final result as A is equal to initial concentration of A e to the power minus kt. These formulas you should be remembering because directly you can apply in the question and you can solve the question very quickly. The next concept is the concept of half-life. Half-life is the time taken for the concentration of A to become half of it. That is concentration of A divided by 2. What we'll be doing here is we'll be calculating the half-life of a zero order reaction and a first order reaction. And for zero order reaction, we know that concentration changes with respect to time following this expression. And for the first order, we know that the concentration of A changes with respect to time following the expression A is equal to concentration of A at time is equal to 0 e to the power minus kt. In this, what we'll be doing is we'll be substituting concentration of A at any time is equal to initial concentration divided by 2, because at half-life, the concentration of A will be initial concentration divided by 2. When we substitute it in zero order reaction, we'll be getting half-life as A0 by 2k. Here you note that half-life is depending upon the initial concentration. When it comes to first order reaction, while doing all these calculations, we'll be getting that half-life is ln2 divided by k. When you notice here, you will be noticing that this half-life of first order reaction does not depend upon any concentrations of A. So, it is a constant. Half-life of first order reaction is a constant. You should also note the value of ln2. ln2 is 0.693. And this is the summary of the entire zero order and first order reaction. Let's say you have a reaction where A is getting converted to different products. Rate is written as k concentration of A to the power n. N is the order. If n is equal to 0, it is zero order. If n is equal to 1, it is first order. Rate is equal to k. That is, rate is a constant in zero order reaction. It does not depend upon the concentration. Rate is equal to k into A for first order. And this is the expression how concentration of A changes with respect to time in zero order reaction. And A is equal to A0 e to the power minus kt is the expression of concentration with respect to time in the first order reaction. Half-life we saw A0 by 2k, 0.693 by k. This concept, time of completion, time taken to 100% completion of the reaction. In zero order reaction, it is A0 by k, which is twice half-life. Note that as well. In case of first order, it takes infinite time. Average life of first order reaction is 1 by k. Time of completion of first order reaction is infinity. Theoretically, it does not complete. It is never going to complete in any time. Examples of zero order reaction is decomposition of gas on metal surfaces. An example of first order reaction is radioactive decays. All the radioactive decays will be following the first order kinetics. We'll be looking this in physics as well. In physics, nuclear physics, this will be coming. This question helps you to get more clarity on half-life and rate of the reactions. Let's do it now. The rate of the first order reaction is 0.04 mole per liter per second at time equal to 10 minutes. And it is 0.03 at time is equal to 20 minutes. We are supposed to find the half-life of this reaction in minutes. We know half-life of the first order reaction is given by ln2 by k. ln2 is 0.693. In this expression, we should find only k. If we know the k, we can substitute over here and we will be getting the half-life of the first order reaction. We know rate of a first order reaction is written as rate is equal to k into concentration of A. We are given with two different rates and two different concentrations. Let's write that now. 0.04 is equal to k into concentration of A at 10. 0.03 is equal to k into concentration of A at time is equal to 20. To find the final concentration, we know how concentration varies with respect to time in case of first order. It is given by the expression At is A0 e to the power minus kt. A0 is the initial concentration. We'll be substituting this over there. When we substitute, we'll be getting 0.04 is equal to k into A0 e to the power k into 10 into 60. Because k usually we'll be writing in seconds and we'll be converting this to seconds as well. 10 into 60 will be giving us the time in seconds. Same thing goes for 0.03 equal to k into a naught e to the power minus k. Time is 20, so 20 into 60. Now what we'll be doing is we'll be dividing this both expressions. When we'll be dividing these expressions, we'll be able to find k easily. 0.04 divided by 0.03 equal to e to the power minus k 600 plus. Why this plus comes is when this minus k into 1200 goes to the numerator, it will become plus k into 1200. We'll be getting e to the power 600k. And when you simplify this equation by taking ln on both sides, you will be getting ln 4 by 3 is equal to 600k. ln of e to the power something is that something. You should know those basic log properties actually. Then when you do these operations, you will be finally getting the expression of k. After you know the value of k, you can substitute it into the expression of t half and you can easily get the value of t half. Hope you will be able to do this. Make sure that you do this and get the final answer as 24. Most of the students will be facing trouble in the logarithmic part. So here are few properties and values that you have to remember to ace this exam. First property is log of a plus log of b will be log of a into b. And if you have log of a minus log of b, it is log of a divided by b. Basically, addition turns to multiplication, subtraction turns to division. When you have an exponent that is a to the power small a, you can bring that small a out of this. Basically, what we done over here is applying all these properties. When you apply all these properties, you will be able to solve these kinds of questions very quickly in the examination. Note all these properties and also make sure that you make a table of these values and remember. In this case, some values were given in the question. Some cases they won't provide the question, so in that case you should remember all these values. You should also note that ln of a is equal to 2.303 into log of a. Here we were given with the log value. ln is over here, so we'll be converting this ln to log by multiplying it with 2.303. ln of a is equal to 2.303 into log of a. When you multiply that and apply, you will be easily getting the answer of the previous question. Make sure you do that question and let us know in the comments. The next method into consideration is the half-life method. Over here, we should note that for any nth order reaction, half-life is directly proportional to 1 by concentration of A naught. That is the initial concentration. Initial concentration of the reactant raised to the power n minus 1. So for zero order reaction, when you put n is equal to 0, it will become T half is directly proportional to the initial concentration. And for the first order reaction, n will be equal to 1 and n minus 1, that will become 0, and hence there will be no dependence on the initial concentration that we saw while we were discussing about the zero order and the first order reaction. Now this is a general reaction and we don't know if it is zero order or first order. But if we are given with two different half-life and two different concentration, similar to the thing which we did in the initial rate law method, the same thing which we'll be applying over here. We'll be writing two expressions for T half and dividing those two expressions and we'll be getting the order. We'll be looking that now. Let's say there is two different initial concentration, that is A naught and A naught dash, and we'll be getting two T half. One is T half and other is the T half dash. We know that T half is directly proportional to 1 by initial concentration, and when we divide both these expressions, we'll be able to figure out n minus 1, and all these T half dash, A naught dash will be given in the question. And from this, order can be calculated because n is the order over here. I hope you got this method. The next method is unit method. In this method, we'll be looking into the unit of the rate constant. We know rate is equal to K into concentration of reactants raised to the power some exponents. So from this, we'll be writing K as rate divided by concentration raised to the power exponents. And X plus Y will be the order. So for zero order reaction, X plus Y will be 0. So K will be equal to rate divided by concentration to the 0. Concentration to the power 0 will be 1. So K is equal to rate. And for first order reaction, X plus Y will be 1 and K will be equal to rate divided by the concentration. Let us take the case of first order reaction. In the first order reaction, we know that rate of the reaction, the unit of the rate of the reaction is moles per liter per second. That we'll be applying here. And concentration of A. We know for the first order reaction, it is dependent on the concentration of A raised to the power 1. So it will be moles per liter. Concentration will be expressing using moles per liter. That is the unit of the molarity that's generally used, and moles per liter. So moles per liter from the numerator and denominator will be cancelling out, and second inverse, that is 1 by S, will be the unit of the rate constant of first order reaction. So when you see a rate constant with 1 by S as its unit, you can predict that it is the first order reaction. This is the list of units of the rate constants. For zero order, it is moles per liter per second. For first order, it is second inverse. You need not remember this. You can practice this 1 or 2 times the same way which we did for the first order. You can do this and you can calculate and you can figure it out. Hope you will do this and you got this method. Now we will be plotting 3 different graphs for first order and zero order reaction. Let's start. First one is rate versus concentration. For zero order reaction, we came to know that rate is a constant thing. So when we plot a graph between rate and concentration, we'll be getting a straight line which is parallel to the x-axis. And in first order reaction, rate is directly proportional to the concentration of the reaction. So when we draw the graph between rate versus concentration, it will be a y is equal to x line. That is, it will be passing through the origin at an angle of 45 degrees. It is the y is equal to x graph. The next one is concentration versus time. This graph tells us how the concentration of the reactant varies with respect to time. For zero order reaction, we came up with this expression, and when we plot this graph, it will be decreasing and it will be reaching 0 at a point. Initially, it will be A0. A0 is the initial concentration. For the first order reaction, when we plot this is actually an exponential decrease. But you should notice that this graph does not reach a 0 at any time. That's what we saw, the full time. That is the time taken for the completion. It will be infinity in this case. And what we'll be doing is we'll be plotting some different graph for first order. We'll be taking log on both sides. First we'll be taking ln on both sides and we'll be getting this expression. And when we convert ln using the formula ln is equal to 2.303 into log, that formula, we'll be getting this. And now we'll be plotting the graph between log of A, log of concentration of A versus time. In that case, we'll be getting a line with negative slope. I hope you got this. The next one is the half-life versus initial concentration. First order reaction, we came to know that half-life is 0.693 divided by K. It is a constant thing. It does not depend on the initial concentration. For different initial concentration, if you are getting same half-life, it is first order reaction. That's what we'll be interpreting from the data of the question. When we plot the graph for this, it will be a constant graph. It will be a line which is parallel to the x-axis. When it comes to zero order reaction, half-life is given by A0 by 2K. It is directly proportional to the initial concentration. So the graph will be x is equal to y line. I hope you got this analysis. Moving on, we will be doing some different kind of analysis. Until now, we were analyzing a reaction using concentration. Now we will be analyzing a reaction with the pressure changes occurring in that reaction. As I mentioned, for gaseous reactions, the progress is monitored by pressure. From the ideal gas equation, we know PV is equal to nRT. So pressure is equal to N by V RT. If constant temperature is maintained, pressure will be directly proportional to the concentration. Note this. We'll be using this concept over here. Now let's say you are given with a reaction. A is giving you B plus C, and at time is equal to 0. That is, at the initial stage, the pressure is only due to A because B and C are not found. The total pressure will be only because of A. Now what happens, as the reaction proceeds forward, some of the amount of A will be consumed and the pressure due to that will be reduced. That is written over here, P0 minus PR, and the same amount of the pressure will be for B and C. Here it is 1 into PR and 1 into PR for B and C because B and C has stoichiometric coefficients 1. If it is 2B plus C, it will be 2 PR for B and PR for C. We already know that concentration of A is equal to A0 e to the power minus KT. One more thing which you have to notice, this pressure analysis, the gaseous reactions, all are first order reactions. That also you have to know. So this is the concentration expression for the first order reaction. As we know that pressure is directly proportional to concentration, we'll be able to write pressure of A. That you have to know. This is not the total pressure, by the way. P is the pressure of A at any time. That is equal to P0. P0 is the pressure of A at time is equal to 0. P0 e to the power minus KT. Now we'll be quickly solving the current year question, that is 2024 PYQ. The following data were obtained during the first order thermal decomposition of gas to a constant volume. Here we are given with A is giving 2B plus C. and at time is equal to 0, the total pressure is 0.1. At time is equal to 115, that is 115 seconds, the total pressure is 0.28. Now we'll be taking P naught as 0.1 and final P as 0.28. Time is 115 seconds. Then we'll be substituting everything over here and we'll be easily getting the answer. But if you do like this, it is completely wrong, because in the question we were given the total pressure, but in this expression what we have to substitute is the pressure of reactant only. That's what I mentioned in the previous slide as well. So what we'll be doing is we'll be considering such an equation. A, the pressure initially is P, and B and C, there is no pressure initially. As time progresses, that is at time is equal to 115, some A will be consumed and that will be appearing in the product side. P minus X is giving you 2X. This 2 is because of the stoichiometric coefficient, and 1C, that is 1X. Now what we'll be doing is we'll be taking the total pressures. At time is equal to 0, P total is P, and it is 0.1. That is given in the question as well. So this will be the pressure of the A, that is pressure of reactant initially. So this we will be taking as P naught as well. Now at T is equal to 115 seconds, total pressure is given as 0.28. And we know from this, when we add this much, we will be getting P plus 2X. So P plus 2X is equal to 0.28, not the pressure of A. So we'll be calculating X and we'll be calculating the pressure of A at time is equal to 115 seconds. Pressure of A at 115 seconds is P minus X. So when we substitute the X over here, we'll be getting 0.01 atm as the pressure of A at time is equal to 115. That is P. And now when you substitute all these calculated values into this expression, we'll be easily getting the value of K. That's what they asked. They asked us the rate constant. Rate constant is 2 into 10 to the power minus 2 second inverse. Second inverse, notice 1 by S is the unit of rate constant for the first order reaction. That's what we saw in the rate method as well. And answer will be 2, because X into 10 to the power minus 2, what is the value of X they asked? So answer is 2 over here. I hope you got this. The next question also is based on the same concept. This was also asked in 2024, 31st January, shift 1. Integrated rate law equation for the first order gas phase reaction is given by. Now they have asked as a general equation. They have asked us to find the equation of K. Previously they were asking us to find the exact value of K for some data given. Here they have asked us the general data. I hope by the concept which we have learned till now, you will be able to solve this. And when you do the calculation and when you solve this question, you will be getting the final answer as D. For detailed solution, make sure you join our Telegram group. I'll be posting the solution within 2 days. Hope you will be joining us in the Telegram community as well. The final topic for this chapter is Arrhenius theory. This theory tells us about the variation of rate constant with temperature. And it is given as K is equal to A e to the power minus EA by RT. What are these constants? We'll be looking at. K is the rate constant, A is the Arrhenius factor or pre-exponential factor, EA is the activation energy required for the reaction to happen, R is the gas constant, and T is the temperature. And one thing you have to notice, the temperature always has to be substituted in Kelvin. Don't forget that. And now, if we are given with 2 different temperatures, that is T1 and T2, and we have 2 different rate constants, K1 and K2. We'll be given with any 3 of them and we'll be asked to find the other one. Then in that case, what we'll be doing is we'll be writing this Arrhenius equation 2 times. K1 is equal to A e to the power minus EA by RT1 and K2 and T2. Then we'll be taking ln on both sides and we'll be subtracting these equations from each other. Then we'll be getting the final result as this. I don't recommend remembering these results. What you can do is always you can derive this thing easily from the original equation. I hope you got this. We'll be quickly solving a question on Arrhenius theory as well. This is a 2024 question for a reaction taking place in 3 steps at same temperature. This is a multi-step reaction, but it is taking place at the same temperature. As we have different step will have a different rate constant. And the overall rate constant is given as K1, K2 divided by K3. We have given us EA1, that is activation energy for 1, 2, 3 as 40, 50, 60 respectively. We have to find the overall EA in kilojoule per mole. we know that K is equal to A e to the power minus EA by RT. So when we write the equation K is equal to K1 K2 by K3, when we substitute the values of K and K1 and K2 and K3, we'll be getting this expression. And when we rearrange, we'll be getting this. And when we compare the value of EA, left hand side we will be having the overall EA, and right hand side we'll be having the overall EA in terms of individual EAs. So EA1 plus EA2 minus EA3 will be the overall activation energy. So when we substitute the values and get the answer, it will be coming as 30. So 30 kilojoule per mole is the correct answer for this question. I hope you got this. Make sure that you join our Telegram channel, wherein you will be getting the notes of this session. And I hope this video was very helpful for you. And for more such videos, say subscribe to our channel and keep watching. Thanks for watching.